Yo yo, what's good? How we doing, Hannah? Hannah, man, it's been a while since I've said your name. Um, I was tempted. I was like, while I was changing, because I just got back from UT Southwestern. I was thinking like, yo, wait. First of all, remember you said I think we both said we wanted to go to UT Southwestern. You said you wanted to, and I think I already knew I wanted to, but it was cool that we both wanted to go there. But I'm gonna be honest, bro, Hannah. UT Southwestern is not a great place. It kind of sucks. It really does suck. I mean, if you want me to get into it, I can tell you. But anyway, back to what I was saying. I was thinking I wanted to hook up my camera and stream like how I usually do on my main channel. I was tempted. But then I remembered the core, the essence of this channel. It's just the simple art of, the basic studying, not none of the bells and whistles of the other thing. No hooking up my screen recorder overlaid on my camera with the screen of saying like I'm locked in right now, like all that overhead, cutting back. And I think I've had higher quality streams because of it. Obviously, the fact that some things have a mic and some don't, me talking, it's a lot less engaging, that's for sure. But look at the consistency. Look at the consistency. It's speaks for itself. So, yeah. Let's I'm streaming, so let's jump right back into it, right where I left off. Dang, the monotony of this is crazy. But that's the joy. That's the joy of studying, especially for things like this. Especially for the career like the one I chose. What career are you getting in now into? Sorry, I'm just yapping because I'm setting up my computer, but what career do you want to do? Because since we haven't spoke since then, and I'm not sure if any of the rumors are true, I'm curious. What did you decide to get into? Are you just not sure right now? Are you gonna go back into pre-med? I hope you do something easy that also makes you happy. I got an at I don't know how to pronounce it. ACI? Acai bowl. Acai. I got an acai bowl.
Acai bowl.
And acai bowl, it's looking delectable. I put some Greek yogurt on it, granola bits, honey, and I'm gonna be honest with you, I put 3 squares of Hershey's chocolate on it too. Oh, I am devious for that, but it was there. That's why I always think, whenever I live on my own place, I'm just not gonna buy junk, and I feel like that's the most surefire way of not putting junk in my body, because I'm not buying any junk. You know what I mean? Unless I go out of my way to buy junk, but it's pretty easy to control myself in situations like those because the pain of spending is too high for a person like me, especially on junk. That said, I should probably get started on this. So silent. The yap is real.
In this video, we'll be covering reaction rates, discussing factors that can change rates. So a reaction rate is how fast or how slow a reaction is going to run. Now, this means that you can measure it in one of two ways, either by the rate that the reactants are used up or the rate that the products are created. Now, either way, these reaction rates are expressed as a function of changing concentrations per change in unit time. So for the reaction R reactants go to P products, what you'll see is we can show the rate as a reaction-based rate, as a change in the concentration of reactions per unit time, or as a change in the concentration of products per unit time. Now, if you're dealing with the rate of reactants, that will be the disappearance of reactants, so you have a negative sign. And it will be the appearance of products, so you have a positive sign. The coefficients are going to be normalized out by dividing the coefficients on each term. So the P coefficients of products and the R coefficients of reactants. Now, chemistry seems almost like magic, really. When you were little, you could make it seem like magic. You'd mix some vinegar and some baking soda, and boom, stuff would bubble and fizz. You mix two things together, and if you're lucky, you get what you really want. But even magic has to follow a set of rules, and chemistry is no different. So for chemistry, these rules are that their reactions have to follow a specific path. And these are the first: the reactants must collide for the reaction to occur. The more molecules there are, the faster they'll to bump in, hold the key in the right way, which lowering the activation energy. Against it. And its proports proper, lower the better the rate proportional to temperature. Lower activation, likely the known as little. Either way, they have to have enough to make the reaction happen. So that brings us to the rate constant. Now, the rate constant is known as little k, and it's part of the rate equation. What's the rate constant is the proportionality constant, and it's proportional with the chance that a collision will result in a reaction. This means that a collision would have enough energy as well as proper orientation. Now, the rate constant little k is going to be indirectly proportional to the activation energy. The lower the activation energy, the more likely the reaction is to occur. The more likely it is to occur, the better the rate constant is going to be. And remember, adding a catalyst will also lower activation energy. Now, the rate constant is going to be directly proportional to temperature. The warmer something is, the faster the molecules move, the better the chance that they're going to hit in the proper way. Now, the rate constant is completely independent of concentration. Because it's a constant, it doesn't matter how many of the molecules you have. It's giving you the probabilities that those molecules are going to get together regardless of how many you have. In this video, we looked at reaction rates and the factors that affect those reaction rates and how to utilize and using experimental calculation. Now, before we jump into this, and you get all worried about experimental calculations, I'm not going to ask you to set up a lab next to your computer. On the MCAT, you're going to be given all the data that you could possibly need from an experiment without any of the math, or without having to do so many dishes. So let's look at this ninth. So let's go ahead and take a look. Now, when looking at this in terms of A, we're going to notice that in trials 2 and trials 4, A changes appreciably, but neither B nor C changes much. We'll also notice that the rate doubles so that when we double the concentration of A, we double the rate. This means that there's going to be a one-to-one relationship between the concentration of A and the effect on the rate. So the rate will be first order in terms of A. Next, we can move in terms of C. C. If we wanted to find out the reaction in terms of C, we need to find two equations, where C is the biggest thing changed. Now, after giving you a minute, Reactions 1 and 3 seem the most appropriate. If you notice here, C doubles, where A and B stay moderately the same. And what you'll notice is the reaction rate is actually almost going to quadruple. Quadruple, you say? Well, that doesn't look like it's quadrupling. Well, let me show you this. This exponent here is 10 to the negative 4. And a good tip on the MCAT is to always convert these so that they're all at the same number. If that was the case, this value here would actually be 20 times 10 to the negative 5. And 20 times 10 to the negative 5 could be rounding error from 1.6. So it definitely goes up. And it goes up by more than double. So as the constant, the rate at least quadruples. This means that in terms of C, the reaction is going to be second order. You're basically going to be squaring the results. Now last, we have to determine B. So looking at two trials, we have to find two where B changes and very little else does. This is a little bit more tricky. And it's much more subtle, but you'll notice that from 1 to 2, B changes a little bit. It changes by 10%, and that's the most we see changes. There's no other change to the rate, though. It remains exactly the same. And so because B really has no effect on the rate, B is zeroth order. So what happens is, we can then put those together, and we determine that the rate is equal to rate constant, little k. Again, A to the first, B to the 0, and C to the second. Now, oftentimes, you won't even see them include B to the 0 because anything to the 0th power is in fact 1. So now, in general, here are the steps you're going to want to follow to determine the rate law using experimental data. First, you can write the generalized rate law, kind of like you saw in red, where you have rate equals k. The second step, e times 10, doing was 0th order, so we don't have to worry about the rest. Any values that you calculated and determine the rate constant. You would simply use the reaction here, rate equals little k, times A to the first, times concentration is C squared. And you would pick any one of these trials, say trial number 3, and you would fill in this concentration for A, you'd fill in this concentration for C, and you would fill in the rate over here, and you could calculate little k. It doesn't matter which one you use, they're all going to lead you to the proper answer. So in this video,
Test. Test, test, test. I don't know if you noticed, but I stopped studying late at night. It's been nice. What?
In this video, we will be looking at the strengths of acids and bases. Acids are defined as either a species that can donate a proton or one that can accept an electron pair. This also makes them electrophiles. Bases are something that will either accept a hydrogen ion or one that will donate electron pair. This makes them nucleophiles. But when you're looking at acids and bases, how do you tell which one is stronger than the other? When you're looking that will donate electron pair, this makes them nucleophiles. But when you're looking at acids and bases, how do you tell which one is stronger than the other? The only way to tell which one is stronger than the other is to learn a few rules. The first rule is this: in the more positive charge something has, the greater its acidity. So looking at ammonia versus ammoniums, it's clear that ammonium is going to be the better acid. It has the extra proton to give. When comparing iron 3 versus iron 2, you'll see that iron 3 is a much better acid because it has a greater positive charge. In addition, the electronegativity of the atom attached to the proton also affects the acidity. So in looking at water versus methane, you'll see that water is much more acidic because it's next to the oxygen instead of next to a carbon. Likewise, looking at H2S and HCl, we will see that HCl is much more acidic than H2S because chlorine is more electronegative than sulfur. Last, size affects the acidity as well. The larger the atoms, the more acidic it is since it's more able to accept electrons with less repulsion. This means that HI is more acidic than HS. As it turns out, HI is a strong acid, and HS is a weak acid, acidic than water. Now, in general, the trend of electronegativity is more pronounced within a period, and the size trend is more seen within the family. Now, to determine base strength, you have the family. Now, to determine base strength, you have to look for the one with the greater negative charge. The greater the negative charge, the better the ability to donate those electrons. So OH minus is a better base than water. CO32 minus is a better base than HCO3 minus. Now the trend for CO3 to donate those electrons. The greater the negative charge, the better the ability to donate those electrons. So OH minus is a better base than water. CO32 minus is a better base than HCO3 minus. Now the trend for electronegativity is backwards for base. The lower the electronegativity, the greater the basicity, to be more basic than HS, and CH3 and H2 is also more basic because it's able to donate electrons. Finally, again, the trend is opposite for bases and acids. The smaller the atom, the stronger of the base. That means that F- is a stronger base than I-, and OCH3 is a better base than SCH3 because it's smaller and wants to donate electrons due to repulsion. Acids. For you have to is more acidic than water. Now, in general, is more seen within the family greater negative charge. The greater the negative charge, the better the ability to donate those electrons. So OH minus is a better base than water. CO32 minus is a better base than HCO3 minus. Now the trend for electronegativity is backwards for base. The lower the electronegativity, the greater the basicity. So NH3 is going to be more basic than HS, and CH3 and H2 is also more basic because it's able to donate electrons. Finally, again, the trend is opposite for bases and acids. The smaller the atom, the stronger of the base. That means that F- is a stronger base than I-, and OCH3 is a better base than SCH3 because it's smaller and wants to donate electrons due to repulsion. Now here's a list of some strong acids and bases. These are things that you will need to know for the MCAT. Remember that strong in chemistry
This is a brief tutorial on how to memorize the 7 strong acids and the 6 strong bases. First, I need to make sure my numbers are correct because I suck at counting. So 1, 2, 3, 3, 3, 4, 4. All right, but let me say hi. Class is pretty boring. I would skip until class is over twice. But no. So I'll stay and add my hydrogen. When I'm done with that, I'll double check. Always add your hydroxides for your bases. And this is the second half. And like Nathaniel knows, California surely is bad. There you have it. Your 7 strong acids and 6 strong bases.
crazy. Sorry, I completely like, whew, that was wild. Jiba Liba, okay, SR. Strontium, no. Jiba Liba, that was crazy. I'm blown away.
Refers to things that can dissociate easily. And, in fact, on the MCAT, strong means dissociates 100%. Now, if you can remember these, you'll be in really great shape. Your strong acids. And your strong acids are going to be all of the hydrofluorines, all of the halogens except fluorines, as well as nitric acid, and the perchloric acids. And of course, watch out for diprotic acids. Remember the cute rhyme, this boy drank from a test tube, but he shall drink no more. For what he thought was H2O was H2SO4. H2SO4 is a very, very strong acid. Now, on the base side, you have your oxygens and your oxygen-containing.
I've actually been burnt by sulfuric acid. The scar has gotten more devious over the months. When was it? A year ago? It was in the spring. Spring, sophomore year. Scar's gotten bigger. Crazy. I think it hurt. I remember it hurting.
You're also going to have your amides and your esters, and most of these, unfortunately, and your hydroxide here. Most of these, unfortunately, you just have to remember. Remember that it can be a diprotic if paired with a 2+ metal cation as well. So again, strong acids and strong bases. Here's your list and you just have to learn them. So in this video, we looked at some of the strong acid and bases that uses. Here's your list and you just have to learn them. So in this video, we looked at some of the strong acid and bases that you need to learn and memorize. And we looked at some of the strong acids and bases that you need to learn and memorize. In this video, we will be looking at the autodissociation of acids and bases, pH and POH. Water is truly an amazing substance. I mean, first, it can take all forms, like the ice or steam or water, fairly easily. And second, we need it to live, which I guess should have been first. And last, of course, it can be both an acid and a base, which makes it amphoteric. So water is pretty much a super molecule for us. So water can act as both an acid or a base. It can be a proton donor or it can be a proton acceptor. And this is what the autodissociation looks like. Two water molecules are in equilibrium with H3O plus, the acid, and OH minus, the base. Its equilibrium expression should be concentration of products over concentration of the reactants. However, all of the reactants are going to be pure water. And pure water is the liquid. and therefore not included in the equation. Kw is just the concentration of H3O plus times the concentration of O minus. Now it's given a special designation known as Kw, and Kw is always a constant. It's always 1.0 times 10 to the negative 14th. If you're at standard state, now standard state, or standard conditions, are room temperature, which is about 25 degrees Celsius in 1 atmosphere. Now, in addition, Kw turns out to always be the concentration of the acids times the concentration of the bases. Or, in our case, the equilibrium constant K times equilibrium constant Kb for the reaction. So once you know this number, you can always use 1 times 10 to the negative 14th to interconvert between Ka and Kb. Now, I'm going to take a little side note here. Back in the day, when you were learning math, you learned a great tool known as a function tool. And that function tool said that f of x, let's say, was equal to x squared, and that this little f meant whatever you put in the parentheses, this is what you would do to it. Well, in chemistry, we have the same thing. Our function symbol is a little p, and our little p says that anything that comes after that little p, you take the negative log of that thing. So in this case, we would take the negative log of x. If we had p10, we would take the negative log of 10, and so on and so forth. So the problem, when we deal with acids and bases, is numbers like 1.0 times 10 to the negative 14th are really hard to understand. They're really small or really big numbers, and so what we do is we use this function to put them into base 10, and it makes them more tangible as numbers. And so when we take the p of the Ka, we get the negative log of the Ka, and this is known as pKa. And we also have pKb, which is equal to the negative log of Kb. So now that we know how to use little function p, we can actually take the negative log of the expression, up here. And what we end up with is pKw is equal to pKa plus pKb, which is equal to 14. Now this is a much easier way for you to interconvert. You can do it mostly in your head, but remember, it's really only useful if you're at standard conditions, 25 degrees C in 1 atmosphere. It can only be used to compare the strengths of conjugate acids and bases to one another. Keep that in mind. So, again, you see the expression for the autodissociation of water, right here. And again, I remind you that water is amphoteric. Now, the problem is that these values, K and Kb, they don't really mean much to people that aren't chemists. They're not on the simple scale. And they can be really big and really small. So what we would rather do is use a term known as pH. And pH is going to be the scale that most people do know. So again, W was simply the concentration of the products, H3O plus times OH minus over the reactants. But in our case, the reactants are pure liquid water, so they're not included. And it was equal to 1 times 10 to the negative 14. Now, if we were to take the negative log of this, again, we're using P as our symbol for that, we end up with pH and POH. Now, pH is the negative log of the concentration of H plus ions, and POH is the negative log of the concentration of OH minus. So if we were to then take these values with the pH and plug them back into the Kw expression, we get that pH plus POH always adds up to 14, just like pKb and pKa always add up to 14. And this is a really great way to interconvert, again, between pH and POH. It also helps us describe the range of the pH and the POH scales, giving us an endpoint to 14. Now, what does pH really mean? Why do we use it to check our swimming pool? Or why do we care? Well, pH can really tell us how acidic something is, on a very simple scale. On that simple scale, being most acidic is 0 and least acidic is 14. And 14 is obviously not very acidic at all. In fact, it's actually basic. Now, POH is just the opposite of pH. And it ranges from the most basic to the least basic. The most basic being 0 and the least basic being 14. Now, on the pH and the POH scale, the value that falls directly in the center, 7. 7 is considered the middle, and it's considered to be a neutral value. Remember, it's only when we're at standard conditions that this scale holds true. If you're outside of standard conditions, it is possible to get a negative pH or a neutral value not at 7 when you're out of the standard conditions. We discussed the autodissociation of water. We talked about pKa and pKb, we looked at pH and POH, and we discussed the relative scale of the pH and pOH values. And bases, and how to relate it to pH and pOH. Now, there are really only 4 types of problems that you'll encounter when trying to calculate pOH and pH directly. And these are going to be to calculate the pH and pOH of strong acids, strong bases, weak acids, and weak bases. So let's take a look at some of them now. Now, we're going to start with strong acids. For strong acids, the acid's going to dissociate 100%. Because it's going to dissociate 100%, we can determine the pH by just taking the negative log of the concentration of the strong acid. The only things you need to watch out for are diprotic acids. If it's a diprotic acid, you're going to need to double the concentration because mole of the acid is going to have 2 moles of protons. This means you can get a negative pH. So let's try an example. What is the pH of 25 milliliters of 0.025 molar H? HCl? Well, using our equation above, all we need to do is we need to say that pH is going to be equal to the negative log of the concentration of our acid, which is 0.025 molar. Well, that's fairly straight.
Oh yeah, the concentration doesn't matter. Oh my gosh. Is 2 point 1 2. So -2, -3.
Straightforward. The problem is, how do you do it? You don't have a calculator. So how do you deal with logs without a calculator? So here's how you're going to do it. First, you're going to make sure that any number you're dealing with is in scientific notation. That means this is going to be 2.5 times 10 to the negative 2 molar. I didn't do anything except put it into scientific notation. Then we recognize based on the law of logs that this is equal to the negative log of 2.5 plus the negative log of 10 to the negative 2. Now, 10 to the negative 2 is something that we would easily know. It would be negative 2. But since it's a negative log, this turns into positive 2. So then what do we do about the negative log of 2.5? Well, we have to assume that since we know the log of 1 is 0, and we know the log of 10 is 1, that it has to fall somewhere between 0 and 1, and we're going to estimate that it's about 0.3. Now, this estimation takes a little time, but you can get used to it and learn how to estimate them. So what we have here is, of course, a negative value, negative 0.3, plus positive 2. So when we add those together, we can get a pH of approximately 1.7. Now again, this is only an approximation, but it's close enough. Since it's a multiple choice test, you'll be able to find the correct pH. So then let's look at strong bases in calculating the pOH. Remember that a strong base is
That product or no? That is multiplied by 2. So this is probably like 4. 4.4, 4.5 minus 4.6, 4.5, 4.6. But times 2. Hey, are you okay? Chichu? Riva? Are you okay? She sounds okay. Bro is singing like there's no tomorrow. She's fine. So multiply by 2. Each part. 8.
going to dissociate 100%. So that means we're just going to be able to take the negative log of the concentration of the strong base to determine the pOH. But be careful. Most of the time you're going to need the pH, not the pOH. So you're going to have to convert, remembering that pH plus pOH is always equal to 4. pOH is always pH have to enter. So you're going to be able to take the negative.
That's true, bro. That's true. Or it's gonna be like 8. So 8.4, 8.5.
Log of the concentration of the strong base is always equal to 14. Again, and double the concentration as needed. Which means you might get a pH of higher than 14, so just be aware. So let's try it. What is the pH of 1 liter of 2.9 times 10 to the negative 4th molar calcium hydroxide? Times 10 to the negative 4 molar. This is going to be the concentration that we will use. Now to solve. pOH.
Just multiply this by 2. 5.8. Which means point. She got 8. I know this is 4. 4 points. 6. 7.5, 7.6.
The log of 5 is about 0.6. So the log of 5.8 is going to be roughly close to 0.7. So we're going to end up with a value here of about 0.7. Again, this is negative and this is positive. And when we get them together, we're going to end up with a pOH me of approximately 3.3. Again, that's probably not
It's 8.6.
Not the end of our solution here, because what we want is we want the
It's out of 14 though, so it's gonna be 9 points. Bro, lock in. Look. Holy muffin, bro. 4 minus 7, 3.3. So 10 points. Yeah, this is 10.7. Holy, oh, what a mess. That was a
pH.
mess.
So we remind ourselves that pH is going to be take 14 and we subtract 7, which shows us is a good check that yes, indeed, this is a fairly basic base because it's over the pH age of 7 and it allows us to intercompare. So in this video, we looked at how to calculate pH for the pH age.
Okay, whatever, whatever. Buffers. Humbly not trying to learn about buffers today.
In this video, we'll learn how to calculate the pH and pOH of weak acids and weak bases. Now, the easiest way to calculate the pH of a weak acid is to use what's known as an ICE table. And ICE stands for initial change in equilibrium. And this is what it would look like for the dissociation of hydrogen cyanide. You would put the acid on one side and the components on the other. Hydrogen cyanide breaks down into H plus and Cn minus. Now, initially, we have our concentration of HCN, 0.2 molar. And initially, of course, we have no hydrogen or cyanide minus. It's a given value. Now, the change, which is not shown, is that for every X molecule you would form of protons, you'd form X, and of course, you'd have to lose X minus moles of HCN, because that's what's breaking apart. So at equilibrium, what you're left with is a value that looks like this. You have your initial minus X moles of HCN, and then you have X molar, H plus, and X molar, Cn minus. Now, the next step to do is to plug those values into your Ka expression, and you're well on your way. Of course, remember Ka for this particular answer would be the concentration of H plus times the concentration Cn minus, all over HCN. So this is what we'd look like. Now, what you'll see is that by plugging in these values, we end up with X squared over 0.2 minus X would equal whatever the Ka was. Now, the problem is, on the MCAT, this is going to give you a quadratic, and you don't have a calculator to solve your quadratic equation. So you're going to always assume that this X is negligible or so small. So small, in fact, that we don't even care about it. So we can just eliminate the bottom X. And now we're left with a much simplified problem. So when you solve for X, you get that Ka would be equal to 0.2, or the initial concentration all square rooted. And this is going to give you the concentration for X. So the X can be assumed to be essentially 0 for all weak acids on the MCAT. Now this is that equation that we just figured out. If you plug the value we got in from the previous page to the pH equation, pH equals the negative log. We end up getting this equation. The pH for a weak acid is equal to 1/2 times the negative log of the Ka times the concentration of the weak acid. There is no difference if you have a diaprotic acid. Again, I'm going to repeat. There is no difference if you have a diaprotic acid. The reason being is because the second proton is so negligible. So let's take a practice over here on the side and see where we come up with. What is the pH of 25 ml of 0.065 molar CH3COOH acetic acid? Now remember, it's very important that you have to know the Ka for a weak acid. And in our case, the Ka for acetic acid is going to be 1.8 times 10 to the negative 5. So let's try solving this one now. So we're going to put it into our equation, and we're going to be equal to, now I'm going to write it as 1, 2, just so that we get that out there, times the negative log of, in our case, 1.8 times 10 to the negative 5. That's the Ka times Wa, or the concentration of the weak acid, which I'm going to write as 6.5 times 10 to the negative 2. Now, I wrote it in scientific notation because it's going to make it easier to do this mathematical problem. So what we do to do this multiplication is we take 1.8 and we multiply it by 6.5. That's almost doubling 6.5. So what we get when we do this math is we end up with 11.7 times 10 to the negative 7. Again, we want that in scientific notation. So that becomes 1.17 times 10 to the negative 6. Awesome. Now we have to solve for pH. So again, our pH is going to be equal to 1/2 times the negative log of 1.17 times 10 to the negative 6th. Now keeping in mind that we don't have a calculator, we have to split out this log. So again, it's going to be 1/2 times all this. The negative log of 1.
I need to walk around for a bit. I'm just walking around thinking about things. Just trying to process a little 5 minutes to refocus in. problem, bruh. This is crazy. Yeah. Okay, see ya. Yeah. Well.
Is the piano custom or is it like a regular one? It's custom. If you need a fall. There he is. There's Don Stuntdouble. Oh. Sean Fellion. What's up? Did you? Sean. No, from the back end. Let's see. It might be hard to just be standing instead of sitting down on something. Yeah. So if you get to the right angle. Before, you don't have to say anything at all. Feel like a horse. Yeah, it's great. It'll be good. I'm John, but that's Pharrell in there. Right. Crazy.
What the heck?
Crazy. Joey Benjo. That's it. But not looking at the camera. That's why I shoot.
Oh, what the heck?
I'm John, but that's Pharrell in there. Crazy. That's Pharrell in there. Right. Crazy. Pharrellian. Well, yeah, it's great. It'll be good. Yeah, I'm. Yeah, it's great. It'll be good. I'm John, but that's Pharrell in there. Right. Crazy. Pharrellian. Joey Benjo. Sit. Not looking for you. That's why your shoes split. I don't know, there's something about stomping the shit out of the old me. Where everybody was like, oh, that's the dad shoe as a joke. That's the dad shoe as a joke. Masculinity, it's all a joke. It's the lawnmower 3000s. So I was like, get the Monarch. There's just a little blood on it on some like custom shit.
the wide to flash the context of it, but it was largely the like actual footage of you. Because we're gonna want to see your face and stuff in it mostly. Got it. But we're just gonna have to have the wide to be like, holy shit, this thing.
Here, this deal this way. Okay. Okay, let's go.
Okay, we're moving on, Frank Johnson.
Venga. Pueden ser. ¿Listos? Permanecen. Y...
Me now, if you need to fall, you don't have to say anything. Ooh, read you like a horse fall. And I've gone back home.
Holy Muppet.
Ooh, read you like a horse fall.
I knew this morning. I was like, oh, we're doing that. The combination of, I feel like when we go in, I think based off the first thing, we can always recapture that feeling. We know it's great. It's great, great, great.
Yeah, but it's gonna be alright. Beef in Mexico.
Beautiful.
The level of professionalism here has been the greatest I have ever worked on, ever in my life, Tapabato.
El nivel de profesionalismo que ha encontrado aquí es lo más que él ha vivido en su carrera, en su experiencia.
When somebody has a vision for a super long time, you can only pray that people care as much as everybody did here.
Cuando uno tiene una visión, uno solamente puede rezar para que la gente tenga el compromiso que han tenido aquí.
The Lord has blessed me with you guys in my life. I don't want to get too emotional about it.
It's a wrap.
If you need me now, if you need me now, I'm black, just depends on where it lands. I'm black, is the read you like
Let's go. Horoscope. Down home, back home. Beautiful. No matter, no matter how. Like a horoscope.
Build what I think. You need to start through the peace. Your time let it be, instead of suffocating crazy dreams.
CH3COOH acetic acid. Now remember, it's very important that you have to know the Ka for a weak acid. And in our case, the Ka for acetic acid is going to be 1.8 times 10 to the negative 5. So let's try solving this one now. So we're going to put it into our equation. And we're going to get that pH is going to be equal to... Now I'm going to write it in this equation. And now we're left with a much simplified problem. So when you solve for x, you get that Ka would be equal to 0.2, or the initial concentration all square rooted. And this is going to give you the concentration for x. So the x can be assumed to be essentially 0 for all weak acids on the MCAT. Now this is that equation that we just figured out. If you plug the value we got in from the previous page to the pH equation, pH equals the negative log. We end up getting this equation. The pH for a weak acid is equal to 1/2 times the negative log of the Ka times the concentration of the weak acid. There is no difference if you have a diaprotic acid. Again, I'm going to repeat. There is no difference if you have a diaprotic acid. The reason being is because the second proton is so negligible. So let's take a practice over here on the side and see where we come up with. What is the pH of 25 ml of 0.065 molar CH3COOH acetic acid? Now remember, it's very important that you have to know the Ka for a weak acid. And in our case, the Ka for acetic acid is going to be 1.8 times 10 to the negative 5.
1, 2. So 1.8 times 10 to the negative 7.
So let's try solving
7.
this one now. So we're going to put it into our equation. And we're going to get that pH is going to be equal to, now I'm going to write it as 1, 2, just so that we get that out there, times the negative log of, in our case, 1.8 times 10 to the negative 5. That's the Ka times Wa, or the concentration of the weak acid, which I'm going to write as 6.5 times 10 to the negative 2. Now, I wrote it in scientific notation because it's going to make it easier to do this mathematical problem, 0.5. So that becomes 1.17 times 10 to the negative 6. Awesome. Now,
This got multiplied piece by piece. Oh yeah, 1.8 is gonna be something like, well, basically almost 2. Yeah, that's true. That's true. That's gonna be -6. Yeah, okay. Wait, -5 because it's gonna be.
now we have to solve for
No, back to
pH.
-7.
So again, our pH is going to be equal to 1 or 2 times the negative log of 1.17 times 10 to the negative 6th. Now, keeping in mind that we don't have a calculator, we have to split out this log to the negative 0, be determining the pH of a, so then we're taking 1, 2 of 6, and we get that our pH is equal to approximately
Half the logs. Oh shoot. I got 1 0. It's +3. Yeah. Okay.
3. Again, this is a multiple choice test, so that will put you enough in the ballpark to find the answer. So, that brings us to determining the pH of a weak base. And just like what we did before, we can actually substitute in the solution for the ice table. After we substitute it in, remember we need to convert into pH. Once we have pH in our hands, then we can use that again. Now, there's no need to consider diprotic bases, since the contribution of the second is negligible to the pH. So when we substitute in for what we had, we can determine it the following way. We get the equation that POH is going to be equal to 1, 2 times the negative log of Kb times the concentration of the weak base. So again, keep in mind, we need Kb. So for methylamine, the Kb is going to be 4.4 times 10 to the negative 4th. This is a value that has to be given to you.
Why is this in pH? Why is the answer trying to be extra? Oh, because this is for the weak base. -5. So 4.4 is probably something annoying like, yeah, something like, it's not even 1. It's just gonna be like point something, 0.1 maybe, 0.2. Okay, so 0.2, and then so that's 4. Yeah, so 3 point something. It's like 1.4. 1 point.
So now let's go ahead and do our math. This one's a little bit easier because all we have to do is we have to take half and we're going to multiplication if you want, or you can estimate it to be a little n to the negative 4. Again, so the negative just fine.
Oh, times 4. Whoops. That's crazy. My bad. Shoot. 0.4 times 4. That's crazy, bro. 40, so 1.1 basically. Do this right now. $76 to 1.76. Grace. Yeah, it looks like one. No, that's one. Sure. Okay, 1.39. Hey, that's what I said. No, that's what I said. And then you have to divide by 2.
If you're uncomfortable, take a little bit off. So we're left with basically 1, 2 of 4. And so our answer here is going to be somewhere in the 2 range. This is not the full answer. That's only POH. So to convert, we need to remember.
No, shoot. Oh my gosh, pH. Oh my gosh, bro. Even in Gen Chem, that shit would get me every time. Sorry, I shouldn't have said that. But actually, why did I apologize? Goddamn.
Remember that pH equals 14 minus POH. So in our case, it's 14 minus 2, or 12. And that makes sense because it's a basic molecule. And we want to make sure we're on the base side of the scale. In this video, we looked at how to calculate pH and POH.
Alright, I'm just gonna dive in a little bit. Is equal to x. Wait, no. KB is equal to, so 1.76 e negative 5, and this is 10m. This weak base. This is just x squared. Yo. So 10 times this. Negative 4. So which one is it? The 1, 2, 3, 1, 2. E negative 4. So 1, 2, 3, 4. That's legit 4 zeros, dog. Wait, no. That's 3. 1, 2, 3. So A. B. Oh, it's squared. Oh, it's squared. It's squared. It's squared. It's squared. It's fucking squared. Okay. Whoops. Yes, so this is a 1e4 squared. 2. So minus 1/2. So it's 1, 1, 2, 0, 1. B. Yo. Was it this video that helped me with that? It's the calculating pH part 2. That's the video that helped me. Oh my gosh. What a headache for one question. Here's to never making that mistake again. I need to take another walk. 34. Let's actually do this one. I'm back. I'm back. Mm-hmm. This is the cure for cancer. Oh, that's crazy. Why they increase? It's non-fibrous, non-cancerous. Non-cancerous.
keys for my phone?
I think so.
Oh my gosh, I think I've cracked the code. Cracked the code.
There, I found this.
Tralalero, tralala.
Bro, why is it using that?
I just put it over here.
Just like this cylinder.
It's okay, it's not stable.
Bro, it's gonna fall, but it's not like it's gonna support the weight of the phone.
Why don't you just put the phone up on the thing next to the whiteboard?
Well, yeah. I need this big.
You need a monitor?
Yeah.
Why don't you just use the iPad?
It is small.
Maybe I should invest in because the iPhone sounds like a really good camera.
Oh, what about this? And then I like low key stack it. Like a final. Alright, I found it. I got it. There's no way they're back already. They're like 15 minutes away. Hello everyone, and thank you for joining me here today. I'm so glad you made time to come here and listen to me present. Or at least that's what you're supposed to do, right? Or no, that's what you think you'll do. And it's what you could do and probably what you should do. I mean, you got up, got dressed, got in your car, and came all this way, but here's a catch. It's so easy to think you're gonna do something and just totally not do it, right? I mean, that's just being human. But then again, not everyone is the same. But technically, we're all the same species and we all live on the same planet. But why does this matter again? Why am I even talking about this to you? Do you even care? Do I care? These are what the average thoughts of a bipolar person could sound like. These are the kinds of thoughts. They can be rapid, disorganized, and sometimes feel all over the place, like a whirlwind of ideas. At times, there might still be moments of clarity or logic, but often it's hard to find that steady rhythm. These thoughts, these behaviors and rhythms are what I decided to study this year, specifically psychotherapy for bipolar patients. As many of you already know, my name is Victoria, and I'm a junior here at Reed. I'm 16 and I aspire to become a psychotherapist, a talk counselor for people with mental disorders. I'm not gonna lie to you, I always knew my whole high school career that at some point I wanted to be an ISM. But for me, settling on a topic of career interest was really difficult. When I was younger, I wanted to be a dance teacher. After discovering that I cannot even touch my toes, my love for animals sprouted into an interest for the veterinary field. I later decided as a freshman that I didn't want to do anything medicine related, so I moved on to biomedical engineering. I was taking PLTW engineering classes at CTE as a freshman and sophomore, so I was interested in STEM at the time, until I found out that I was horrible at physics, so once that was out the window, my interest in career was up for grabs again. Then I took AP Psychology in 10th grade, just for the credit. But as we approached the end of the year, we began to learn about psychiatry and mental disorders. Although the entire course was fairly interesting to me, this topic was different. I mean, we're learning about how different people's minds can be so entirely different. Most people would call people with mental disorders sick and sad, and of course depression and isolation can be tragic, but there's more to this. These people have a brain that works in a different complexity than your average human, and they need help. People stereotype them as unhuman and outcasts, but they're just people like us. And they need even more mental health attention than anyone else, especially bipolar patients because, well, they're literally bipolar. They experience these extreme highs and lows daily. This is what I strive to accomplish in psychotherapy, to make mental clients feel noticed and supported. I took ISM primarily because my brother told me to. It was the reason he could skip school so he could see his mentor. But when I started looking into what the class was actually about, I was taken aback, really. I get the opportunity to experience my desired career before I even graduate high school. Found it insane to me. and is now, in my opinion, the only course so necessary and important to have ever existed in schools. Before I even graduate, so let's look at what the heck I even did this year, shall we? Let's highlight what I've learned through my informational interviews and secondary research sources. So I personally only did informational interviews in disguise of looking for mentors. I mean, my first interview with Miss Wiley was purely informational, but I liked her so much I straight up asked her at the very end of the interview. Anyways, I had 4 total. Let's start off with Raven Lucas, a counselor at Frisco Counseling and Wellness. She was the first professional I talked to through ISN, and here were my main takeaways. She said to take notes of each therapy session with the patient, and that confidentiality is very important to gain trust with your patient. She also said to exclude yourself completely out of the conversations. Next off, we had Haley Wheeler. She was also at Frisco Counseling and Wellness. I really liked her and I even considered her for mentorship. However, her therapy was only for parents, which I felt was too singled out, which is usually fine, but a bit too far from my line of focus. She said that it was important to manage your work and home life. She also said that your well-being has to be good in order to take care of your spouses, and that you should come to work with a positive and anticipating mindset. Next up, we had Brittany Rollin. I actually asked her to be my mentor. She worked with many disordered patients, and I really liked her style of using tactile methods. However, she said she already has a very tight schedule and would not really be able to fairly give me her time, which I obviously respect. She told me to be careful with such topics that may be heavily cultural, social, or political. She told me this because she's also a faith-based counselor, which is something that I was looking for in particular, and during that conversation she brought this up. And she said that background knowledge on brain sciences is needed more than usually expected, and psychoanalysis can best be supported with tactile and verbal techniques, which I mentioned earlier. And last but quite certainly not least, Miss Edna Wiley. Her interview was more of a conversation of what her job looked like, but here are my main takeaways. She said to always have a welcoming attitude and that faith-based counseling differs from regular counseling by a lot. She also taught me about the 6 levels of intimacy pyramid, which I found to be really helpful when it comes to counseling families. At the end of the interview, I told her about what we do in ISM, how the mentorship part worked. We actually worked things out right away and she became my mentor. And she's actually right here too. So yeah, Ms. Wiley became my mentor. We also wrote many research papers on articles that I found on the web, but I just used those to actually learn about what psychotherapy actually is and what its flaws were. After a few weeks of study, all the research that I did this year is listed in my digital portfolio. If you go to the homepage and then click on the research tab, you can find everything right there. I have it on my board also. Alright, so my research this year assisted me in the development of my original work and product in the sense that because of it, I learned about the rarely noticed yet large flaws, and I developed an understanding and desire to develop some type of solution to the problem I noticed, which is the lack of consistent and available support for bipolar patients on empathy psychotherapy. All of my research, I focused on 3 specific disorders because I knew I wanted to choose from which either one of these. So we had major depressive disorder, which required a 2-year full recovery, and cognitive therapy I found was the best treatment for that. My second option was PTSD, which stands for post-traumatic stress disorder, and it required at least a 1 year to make full recovery, and the best therapy option was humanistic therapy, and the last one was OCD, and it required a 1.5 year to reach that full recovery. And the best therapy we found for this was systematic desensitization and exposure therapy, which makes sense. thinking that was put into what I wanted to do. I sort of already had the idea of an interactive journal from the start, and all I really needed to do was focus and kind of learn about what the content should really look like. So the steps for the original work process was actually very clear. I realized the primary reason I wanted to do an interactive journal was because it was different from a therapist. It was accessible anywhere and at any time. You could use it on your phone, iPad, laptop, notebook, and whenever you like, which is contrasting to an actual therapist, because you cannot just call them or talk to them anytime, as their people too. As much as they care about you, they do have their own lives. The journal is also free of any possible bias, judgment, or time constraint. Photos are uploading, but I think it's time we start talking about some of my bits that happened this Wiley. And when we met every other Wednesday after school. We would obviously always get the things we needed to get done, like the mentor handbook, and she would frequently give me feedback on what I think most of the time she would, but I think that most of the time she was just being honest with me and telling me about her experiences as a psychotherapist. She showed me the reality of being a therapist, and she showed indirectly to me the importance of being joyous, patient, and understanding with her clients. She treated me as not just a mentee, but sort of like a daughter. Her welcoming personality gave me the perfect image of what a therapist should look like. Outside of our research time, we connected, and if there's one thing I learned about her is that she loves her family, which I absolutely admire, because I also believe that family is very important. But anyways, I left every single meeting feeling inspired with a smile. The main reason I chose her as a mentor is because of her faith-based roots and beliefs, which is something I will always have rooted in my life. You've impacted me spiritually, and I appreciate that so much. I took my time over the summer before junior year to think about what I would like to do for my product. Considering I was studying therapy, I wanted to create something with therapeutic service that would be available to any client around the world. Obviously, nowadays, to reach the whole world, as a teen, the first step is to head to our beloved internet. First, I wanted to make something that was unique, so I looked into therapeutic sources that were already online. I found websites, articles, games, but nothing that was personal and interactive. So I decided to just use that. Make something that would consist of activities and could be personalized and interactive features, a journal for that part. So I was making a digital interactive therapy journal for anyone, which will be accessible on the internet, actually free on Etsy, and can be used digitally or printed for a more tactile user. So as I reflect on my experience in ISM, I really realize how much growth has happened, both academically and personally. At the beginning of the year, I had an interest in psychology, but I wasn't entirely sure where that would lead me. After months of research, interviews, mentor visits, and building something from the ground up, I feel confident not only in the field I've chosen, but in the purpose behind it. This class taught me how to carry myself professionally, how to communicate effectively, and how to take initiative in environments that are often unfamiliar. But more than that, it taught me how important it is to ask questions, to be open to learning, and to genuinely listen, especially in a field like psychotherapy where those qualities aren't just useful, but they're essential. I wanted to sincerely thank Ms. Wiley, my mentor, for investing her time, insight, and experience into me this year. You've modeled the kind of therapist and person I hope to become, someone grounded in compassion, honesty, and grace. I'm incredibly grateful for your guidance. And to my family, thank you for supporting me through this process, emotionally, logistically, and in every way in between. And to everyone here, thank you for taking the time to listen. It means more than you know. Ultimately, I'm proud of what I've done this year, not because it was perfect, but because I pushed myself in ways that mattered. ISM has given me the space to discover not only a career path, but a sense of direction, and that's something I'll carry with me far beyond high school. Thank you again for being here today. And that's my conclusion, which is all my part. Okay, so that was the presentation. I do have to fill in some slides, and a lot of slides were missing pictures. And this is my display board. It's the same one from Showcase, but I changed the format and the font because I know you were telling me that it looked like it needed to be more cleaned up. So I just kind of recreated it. I changed like the font. I chose to make clean cut corners instead of rounded ones. I also added my LinkedIn, my portfolio QR codes, which I don't think were there before. And instead of having the same jar game that I had before, I'm gonna like actually make a QR code, and I'm gonna make like a Google form where they can fill out a quiz with the same like questions and stuff. But they'll get a score, and I'll still give them candy for there. But I think it's just a little bit more convenient than carrying around the jars. So yeah, I'm gonna glue my QR code down there. And Miss Wiley confirmed with me that she'll be there on Tuesday. She said she might miss the presentations, but she will definitely be there for the slideshows. So Miss going first. I'll be going second. I think she said hers was gonna run around 25 to 30 minutes, and mine we'll have to check, but it will definitely go past 20 minutes. And yeah, that's it. And I'll go over with you maybe during class. I'm not sure, but I'll definitely resubmit. The final presentations that are updated with the steps, and you'll be able to see the pictures with the ones that I already submitted to you. So, yeah. Hello? Hello? Yeah. I'm in the sky. I'm in the sky. No, I'm upstairs. What? No,
Where did you go? Good. Where did you go?
The usual.
Uh,
Wherever mom and dad takes me.
dude, where did they take you?
To a house where we played ping pong. Like this.
Oh, like Indian party?
Yeah.
One party?
How did you think? Hey, did you see a Bible in your car? Like 2 of them?
I saw one Bible, black.
Ooh, I already took that out. We're cooked. Daddy, I'm not gonna see the Bible.
Was that Bible next to my clarinet? Yeah.
Yeah, no, we already took all the Bibles out of the trunk. All the ones that we saw.
Did you check the glove compartment?
Oh, no, I didn't. Did I check that?
I don't know if there is one there, but it's worth checking. If you think a Bible is in there.
Well, I don't think it's worth checking because they once who told me to take it to the car and I put it in the trunk. So I'm not gonna
I get
remind
3
them. I'm not
courses
gonna
right from
remind them.
this.
I'm the one that did that. And CAT's kind of like a star test.
Yeah, they even use the same font. Oh wait, is that? Oh, we're both reviewing MCAT.
Towards me to what?
We're both reviewing MCAT.
Bro.
You're doing it and I'm doing it.
I don't mind if I study for STAR right now. You want to see my STAR tests? Let's go to mine. Bro, this is so goofy.
Did mom and dad bring food?
Think. I'm not hungry. Wait, why are we not connected to Wi-Fi? Hello? Also, why is the dinosaur game not working? Bro, you know the Wi-Fi game. You know the Wi-Fi is bad when the dinosaur game is not working.
You have to press spacebar, bruh.
Oh. Wait, no. Oh, it's working. It's working.
But can you not play the?
It's not working anymore. Do you have any pencil and paper?
Wait, did you finish the library books I gave you?
Yeah, not the read. Not the stories of book one, but I finished the cat one.
Did you like it?
I mean, it was kind of. I already knew what was gonna happen.
Oh, that's rough. You know, there's 2 more in the series, right?
Really? Who's your favorite?
Wait, can you tell me the entire story? What happens?
Okay.
But very quickly.
So the cat is he so he's obviously homeless, right? And so this guy is trying. The kid is trying. I don't know any other names. So like I was kind of like skimming through it. Anyway, the cat doesn't have a home, and so this guy he gets like enriched or something, and then he gets okay. So here's the thing. I kind of didn't read the whole book. I skimmed through it, but all I know is that he goes the blue jay and the frog and the cat. He goes with the guy because apparently he's lost or something, and he's trying to do this spell, and so they have to go and find him to do the spell, and and that they have to do magic to find him. That's all I got from the briefs thing. I'm on page like 56 right now.
So how do you know what's gonna happen how did you know that you knew what was gonna happen if you haven't even finished the book?
Because I read book reviews of it.
Why?
Because I don't know. Did you bring food? He wants food.
Did you bring anything? Oh. I'll see later. It's okay. It's fine. No, it's okay. No, I'm fine, Mom. I'll figure it out later.
paper.
20 hours. Because it takes time for compound 1 to get to the things before it. Oh, that's why there's those increased up in the first place. Did I understand that? Jumping in the first time? Clearly I didn't understand that. Been going for a while. So, that's rough.
Anyway, have fun studying for it. I'm gonna go continue my book that I'm going to read. Bro, is it possible to only read in the night?
Yeah.
Exactly. It's like you never read all the books. You never see with my naked eye. Yeah. Read during the night. One time, I actually stayed up till 1 a.m. reading, and that was approximately 3 weeks ago.
So devious. By the way, when you were taking the video, like, I don't think you pressed record. So when I fixed the camera, that's when I started recording.
I was just gonna submit it now. Oh, I did.
But watch to the end. Oh, I think I accidentally offed it.
Wait, let's see if you missed anything.
That's for the teacher?
No, you didn't miss anything. No, it's interviewers.
You sending that to the interviewers?
No, I'm just sending it to my teacher. The whole purpose of that is to see if you're dressed well. I don't know why you want us to present the whole thing. It's not even done yet.
She didn't even you didn't even show your shoes. Very different. Right, lungs energy. Uh, oh, but this passage was devious. Yes, I clearly didn't understand that passage at all. Look, it's all wrong. 5 devious questions.
Nucleophilic addition reaction, using hydride reducing agent and the Grignard reagent as nucleophiles in the reactions. So to introduce a nucleophilic addition, we want to look at the bonding pattern change that happens over the course of the reaction. What we're going to find is we're going to break a pi bond in the starting material and form two new signal bonds in the product molecule. Now when we're using a strong nucleophile, the way this reaction works is the nucleophile will directly attack the carbonyl carbon, which is electrophilic. It's got a partial positive charge on it. And because we can't have 5 bonds of that carbonyl carbon, we're going to break the pi bond and push those electrons out onto the oxygen. That gives us a tetrahedral intermediate that looks something like this. And you can see that we formed our first new sigma bond between the nucleophile and the carbonyl carbon. Now the second sigma bond occurs when we do an acidic workup step of this intermediate, and we just add a proton to the extra electrons that are now hanging out on oxygen. So our new sigma bond is here. Now if I don't have a strong nucleophile, it's going to do the attack directly. Then we can instead activate the electrophile so that it's more likely to be attacked. And the way we're going something that's electron deficient, even more seemingly electron deficient, is we want to add a positive charge to it. So we can protonate the oxygen of the carbon using an acid catalyst. And then the nucleophile can attack even if the nucleophile isn't as negatively charged as we saw in the first example. Now we'll still push those pi electrons out onto the oxygen. And now we've done seen breaking of a pi bond and forming two new sigma bonds. We've just done it in the opposite as when we're using the strong nucleophile. So with this general overview of how a nucleophilic addition reaction works, let's take a look at some of the strong nucleophiles that you're likely to see on the MCAT. So firstly, I want to introduce a hydride reducing agent. So you got two options on the arrow here. You can either use something like sodium borohydride or lithium aluminum hydride. What you're looking for here is a whole bunch of hydrogen at the end of the formula of my reagents because that indicates that hydrogen borohydride or lithium aluminum hydride. What you're looking for here is a whole bunch of hydrogen at the end of the formula of my reagents because that indicates that hydrogen has a negative oxidation state. So we've got effectively hydride ion or an H-, that is the reactive species here that behaves as the nucleophile. So as we just saw in the previous slide, we will expect that hydride to attach here and push those electrons out onto the oxygen.
Might just fall asleep on the ground. Holy muffin.
Yo, I forgot I had a white Posca, bro. Yo, I low-key forgot I had a white Posca. I forgot I had a white Posca. Used it for the posters. That's hype. My fat Sharpie. My super fat Sharpie. My scissors are here. Oh, I'm getting really loopy. I'm getting loopy, real loopy. Tired loopy. I'm getting loopy.
reducing agent. So you got two options on the arrow here. You can either use something like sodium borohydride or lithium aluminum hydride. Previous slide, we will expect that hydride to attach here, and to that we'll get alcohol as the final product. So we're actively adding an equivalent of each two across the carbon-oxygen double bond, and that's why this reaction is referred to as a reduction. We have two ways to think about this reaction. We have either fewer bonds to oxygen, or we have more bonds to hydrogen. So in either way, we would call this a reduction. So you might see other reducing agents used on MCAT, but you will recognize hydride reducing agents because they typically have either boron or aluminum in them, because these elements are not very electronegative, and therefore are able to donate those electrons to the hydrogen, giving the hydrogen that sort of negative charge to do the nucleophilic attack. Now when you think about doing this reduction on aldehyde or on ketones either, a functional group reacts, and depending on the starting material, you either get a primary or a secondary alcohol, depending on whether this group out here is a hydrogen or a carbon group. And finally, we can't do a reduction in order to get a tertiary alcohol, because the hydride nucleophile will end up always being attached to what was once the carbonyl carbon. So we can't end up with three carbon groups out here. One of them has to be hydrogen, because a type of strong nucleophile that you might come across would be something like the Grignard reaction or the Grignard reagent. And we can make a Grignard reagent, which is this guy right here, from some sort of alkyl halide, and treating it with magnesium metal. So if you think about the polarization of the carbon-magnesium bond, carbon is more electronegative than magnesium, so it's going to pull electrons toward the carbon. And therefore, again, we have effectively a carbanion being the nucleophile in our reaction. So look like? Well, it's the same kind of mechanism as before. We'll find that all carbonyl compounds react in the same way. Nucleophile attacks the carbonyl carbon, kick electrons up onto the oxygen, protonate at the end, and we're going to get another alcohol as the product here. This time I can get a tertiary alcohol as the product because we're adding in a new carbon group instead of the hydrogen down here. So as a summary, our organometallic reagents are going to act as carbanions, and because a carbon with a negative charge is such a good nucleophile and also very basic, we need to make sure that our starting material doesn't contain any hydrogens that are any more acidic than the alpha hydrogens are out here. So anything that has an alcohol in it, or a carboxylic acid in the starting material, will be incompatible with reacting with the Grignard reagent. So you might have to protect those functional groups in order to let this nucleophilic addition occur. So to summarize, we looked at how the carbonyl functional group behaves in nucleophilic additions. And focus on being able to recognize these functional groups in any molecule. Now hemiocetals and acetals form via a nucleophilic addition reaction, where alcohol is the nucleophile. So the overall balanced reaction is indicated here, and while we won't focus on the mechanism in this video, I do want to show that overall we're going to add two equivalents of an alcohol in order to make the final product, which would be the acetal. And an intermediate along that pathway is this group in the middle called the hemiacetal, hemi meaning half. And so I can see that not only am I incorporating two equivalents of my alcohol over the course of the reaction, but I'm also doing it under reversible conditions because alcohol is not as good of a nucleophile as some others out there, like a hydride reagent or an organometallic reagent, so we're going to activate the carbonyl compound using an acid catalyst, which makes every one of the mechanistic steps reversible. Now the big thing that I want to focus on for this particular video is that you're going to recognize either a hemiacetal or an acetal by looking for one carbon that's bonded to two other carbons. So you can see that that bonding pattern is true for both of these functional groups. And the thing that distinguishes them is that hemiacetals have one OH group attached to one of those oxygens and one OR group attached to the other one of the oxygens. Notice that it doesn't matter what's connected down at the bottom, whether you started off with two carbon groups here like a ketone, and then we have to distinguish between what those oxygens themselves are bonded to. So in the first molecule here on the left, I see that this carbon right here has bonds to two different oxygens, and both of those are OR groups. Just because it happens to be cyclic doesn't make a difference, and so this is an acetal, and the molecule below it has a similar situation where I've got one carbon bonded to two oxygens. But now we've got an OH group here, and so this thing would be a hemiacetal. Now if we look at the molecule at the bottom, this straight chain guy here, we see carbons and oxygens, and two oxygens in neither of these oxygens or a hemiacetal. The functional group that I would call this would be an ether, so I actually have two ether functional groups in this compound. That's where I have one oxygen bonded to two carbons, whereas an acetal is one carbon bonded to two oxygens. Now as I complete my counterclockwise circle here, if I look at the next cyclic molecule, I again see one bonded to two carbons, whereas an acetal is one carbon bonded to two oxygens. Now as I complete my counterclockwise circle here for functional groups in this compound, that's where I have one oxygen bonded to either an acetal or a hemiacetal. The functional group that I would call this would be an ether, so I actually have two ether functional groups in this compound. That's where I have one oxygen bonded to two carbons, whereas an acetal is one carbon bonded to two oxygens. Molecule, I again see one carbon bonded to two oxygens, and both of those are OR groups, so again you might expect this to be an acetal. Notice now that the carbon in the middle has two hydrogens attached to it. Doesn't change that this is still an acetal functional group. Remember, it's not what's bonded from the original aldehyde or ketone. It's what's connected to these oxygens here that determines what the functional group is called. And finally, here is a much more complex molecule than all of the others, where I have a lot more oxygen in the molecule. So remember, we're looking for one carbon that's bonded to oxygens. So as you search through, you should recognize that this carbon right here has an OH and an OR group, and therefore this should be another hemiacetal. Now the other thing that I want you to consider is this new hemiacetal or acetyl functional group was a carbonyl. It was an aldehyde or a ketone. So it's that carbon that is bonded to those two oxygens that used to be the carbonyl carbon. So if we look at all of these molecules and try to deconstruct what they looked like before, you should be able to identify where all the carbonyl carbons were to begin with. So you need to be able to sort of go back and forth between these two functional groups when you're looking at molecules, being able to sort of predict what the acetyl or hemiacetal might look like if you start off with the aldehyde or ketone.
That's crazy. Because yeah, I do believe that they'll ask this. They'll show you this, and then you have to understand it's an acetyl going on. And if you attack right here, this oxygen over here, this hydrogen.
And also, if you have an acetyl or a hemiacetal present, be able to sort of revert back to the carbonyl compound. So as a summary for this video, we looked at how hemiacetals and acetyls were formed via a nucleophilic addition of either one or two equivalents of an alcohol,
Let's just finish this passage. No seals there. This is something I need a fresh mind for. So I'm gonna take this and make a note for myself for later. See